So today is the last bit of this section, and so what we're doing is graphing rational functions. So all that means is things written as fractions. So hyperbolas and truncuses would be an example. All right, so an example is something like this. So this would be what we would consider a rational function, because it's written in fraction form. Ratio, fraction, plus 1 on the end. Plus 1, plus 2, plus 1. That's right. All right, so straight away, when we look at something like this, and we see that there's a term on the bottom, all right, the x plus 1 on the bottom here, straight away, we've already got a restriction on our implied domain. Alright, so because we know always the denominator, always say denominator, it can't equal 0. Alright, for any of these, so whatever it is, the denominator is, can't equal 0. So in this case, it's just x plus 1. So that means that x plus 1 can't equal 0. I take 1 from both sides. X can't equal negative 1. So in terms of the graph, if x can't equal negative 1, it could be a couple of different options. And we'll get to what those different options might be in a minute. All right. Okay. So then the question is, what can we do with this? So what we can do is we can factorise the top. This is one of the things we can do. You can divide it out as well, but I'm going to factorise the top line here. So two numbers that multiply to give us 2 and add to give us 3. 2 and 1. All right, now what do we notice? We notice that we've got x plus 1 on the top and on the bottom, and so they could cancel. All right. Now, because the x plus 1 is on the top and the bottom and cancels out, in the past when we've looked at something like this, we would have said, oh, there was an asymptote at x equals negative 1. But in this particular case, because the x plus 1 cancels out, it presents itself in a different way, and that's why I've got this graph here. So let's not pick that one. Let's clear it all. Clear it all. Clear it all. So we can graph this. Put it on the keyboard. So x squared plus 3x plus 2 over x plus 1. And I'm going to graph that, and I'm going to initialise that zoom. And there's what I get. You see that arrow? Or do I need to twist it? So what does this graph look like? Straight line? Right. So when I cancel those on my left with x plus 2. So when we look at this straight line here, we've got a y-intercept here of 2. Gradient across 2 up 2 is 1. So this is presenting itself looking like x plus 2. Yep, so far. Now the question was, what's going on here at this -1? Because here, that -1 looks like it just goes through there. So, but if I go to analysis, G-solve, and I'm going to do a y calculation for an x value of -1. And what comes up here says that it's undefined. So rather than an asymptote, when you have something that's cancelling it out like that, so when we put these two things together, what that's referred to, so I want to put these two things together, the fact that it cancels out, what that leads to is a discontinuity. So discontinuity at precisely x equals -1. So, how do we draw it? The way we draw it is like this. So at that point, wherever it is, here, at -1, we put a circle. And then we continue our straight line both ways there. Alright, so discontinuity at -1. Now, of course, because of the pixelation and that on our screen, that doesn't appear to be like that. And of course, remember, this is only when x is precisely -1. If it's a little bit either side, then you've got a graph. So it's only a teeny tiny hole. Alright, okay. So whenever you see a factor, top and bottom, you're going to get a discontinuity, as it's termed, rather than an asymptote. If that only appears once, if it was just x minus 1 down here and didn't cancel, then it would be an asymptote. Right. When it cancels, discontinuity. When it doesn't cancel, asymptote. All right, anything about that so far? Okay. All right, so let's have a look at some other examples. All right, so next one. Alright, so this time we've got y equals x plus 2 on x. So when we've got ones like this, so if your power of x on the bottom is equal or less to the power of x on the top, you then need to divide it out or some other technique. In this case, what I'm going to do is use another technique where I'm going to split that up. So if that's x plus 2 on the top, it's the same as x over x, oops, plus 2 over x. Yeah? And x over x is 1, and 2 over x is 2 over x. And so this here looks like a, starts with H, hyperbola. Alright, so up there you're not quite sure what's going on, but then once we've manipulated, now it looks like a hyperbola. And so now we can figure out some things. So now that we've identified that it's a hyperbola. So hyperbola asymptotes. Two of them, wouldn't there? One of them would be x equals 0. The other would be y equals 1. Alright, so let's put our asymptotes in. It's a normal, standard, everyday, apart from those translations, on a bit of a dilation. Hasn't been reflected or anything, so we know it's going to be here and here. So if it's there and there, going across the x-axis, so there's got to be an x-intercept. So if it x-intercepts, y equals 0. Now, it doesn't matter which one of these that you work with. You can work with any version of the thing. I'm going to work with the top one. So 0 equals x plus 2 over x times both sides by x. 0 is going to be x plus 2, so x is 2. So we know that our graph goes like that. So we kind of try and get the same kind of shape over there. All right, now fun begins. Alright, so let's have a look at another one. Y equals x squared minus x minus 6 over x squared minus 1. All right, so first of all, whenever our denominator, we know our denominator can never be equal to 0. So straight away, we can say that it's undefined when x squared minus 1 is equal to 0. All right, we'll find out a little bit later about whether what that's going to mean. Probably in this case I'm thinking asymptotes, because x squared minus 1, if we were to factorise it, it's x plus 1, x minus 1, but this x squared minus x minus 6, if we factorise that, would be x minus 3x plus 2. Right, so there's not going to be anything cancelling out there. So if there's not going to be anything on the top to cancel out with the bottom, then it's going to be asymptotes, not discontinuity. So we have two asymptotes, two vertical ones. X equals -1 and x equals 1. It's very interesting, isn't it? All right. Now, as I said before, if the power of x on the bottom is the same as on the top, then you've got to manipulate it. Because here we've got x squared minus 1, it's a bit more complicated. So unfortunately this time, maybe not unfortunately, it depends on whether you mind dividing or not. So to get x squared, you've got to multiply x squared by 1. And then 1 times x squared is x squared, 1 times -1 is -1. Put that under the 6. Just so that I've got my things with the x's in them underneath each other. So x squared minus x squared is nothing. We've still got minus x there. Minus 6, a minus and a minus is a plus. So it's minus x minus 5. So what does that mean? That means that my y equals x squared minus x minus 6 over x squared minus 1 can also be written as 1 plus what? This stuff. Over what our denominator can be written as that. All right. Then, of course, we could take this negative there and there out, so we could have it as 1 minus x plus 5 over x squared minus 1. That's why I turned off. Didn't turn that on. You've got to turn the power on. All right, with me so far? Yes? All right. So, we've already determined we've got vertical asymptotes. What else do we know? What's this one here tell us? Horizontal asymptote? Is that what you said? All right, so horizontal asymptote. Y equals 1. There's a reflection of some sort, and this stuff's all a bit funky. So let us have a bit of a look at what might end up being. So other things that we can get, we've got some asymptotes. I'm going to up over here, I'm going to draw it up at the top over here. So we've got vertical asymptotes. I'm being lazy here at -1 and 1. Horizontal asymptote at 1. so this is looking a bit funky. So now we need to see if we can figure out some y-intercepts. So that'll be handy. And x-intercepts, if any, again, that'll be handy because that'll tell us, because now we've got 6 different sections here. And so by finding y and x-intercepts, it will tell us which sections have got the graph in them. Yes? No? Maybe? Yep. All right. So I'm just going to work with our original version, x squared minus x minus 6 over x squared minus 1. Just going to work with that. Y-intercept, x equals 0. So let's whack that in. 0 squared minus 0 minus 6 over 0 squared minus 1 is 6. Yeah. So we've got the y-intercept up here. So that's suggesting that we've got part of the graph is up in this skinny bit here. Then for x-intercepts, y equals 0. And so 0 equals x squared minus x minus 6 over x squared minus 1. Times both sides by the x squared minus 1. You get 0 equals x squared minus x minus 6. And I'll factorise that in 4. Minus x minus 3 and x plus 2. So my x-intercepts, or our x-intercepts are where? 3 and 2. Negative 2, I should say. So, x equals 3. X equals negative 2. Now what? What do you think it's going to be? Like? Yes? Does that kind of make sense that it might be like that? Let me... That's what it looks like. They're going to have to, let's drag this down. There we go. Let's move out a bit. There we go. All right. Anything about that particular question? I've got a couple more. All right, yeah, this one's very interesting. Now, sometimes, so here we had asymptotes kind of everywhere. Sometimes asymptotes don't necessarily apply across the whole graph. And we might go, oh yeah, right, okay. So, but the answer to that is, how do you know that? The answer to that is, how do you know it? Is that it appears when you do your working out. So, for example, here's one where the asymptote applies in certain parts but not others. Alright, so in this one, our power on the denominator, x squared, is less than the power at the top, x. So there's no dividing out manipulation to make it more simpler. The only thing that we can do is factorise the denominator and minus 5 and plus 2, I think, would be correct. There's no cancelling out, so that means we've got asymptotes. And we have 2 at x equals where and where? 5 and minus 2. All right. So, So 5 minus 2. So far, so good. Alright, it's not like our hyperbola or truncus or anything where we've got some number out here that's shifted it up or down for the asymptote. So because there's no number out here, it kind of suggests then, and because this is kind of in the form of a truncus, it suggests also at y equals 0 for another asymptote. So it's kind of suggesting that we've got another one along there. All right. Now this is where the interesting bit comes. Y-intercept, x equals 0. So whack that in. Y equals 0 minus 3 over 0 squared minus 3 times 0 minus 10, which should be 3/10. Yes? So down here. We haven't got much to work with here. Now, ordinarily we'd say, all right, there's a asymptote there, so there shouldn't be an X-intercept. However, as I mentioned before, sometimes the horizontal asymptote kind of only applies in parts of the graph. And this is one of those. So our X-intercept is when y equals 0. And what have we got? We've got 0 equals x minus 3 over x squared minus 3x minus 10 times both sides by, you get x minus 3. And so x equals 3. So we're, in this case, we're getting an intercept here in that section. So our asymptote doesn't apply in that middle section of this particular graph. Now what I didn't do is I could have gone up here, I could have said, all right, let me split this up into 2 bits. The 2 bits being that. All right, so it's not just a simple kind of hyperbola thing. It's got these 2 bits that we're looking at, or a truncusy thing for a square. It's because we've got these two bits. So it's complicated things a bit more. So then the next question is, well, where does all this stuff go? All right, so where does all this stuff go? So you might just pick a value so that you know where it goes. And let's say I'll pick a value. Let's find out what's going on over here. Because when we find out what's going on over here, we'll then be able to work back. So what's going on over here? So let's sub 6 in. So when x equals 6, we've got y equals 6 minus 3 over 6 squared minus 3 times 6 minus 10. So 3 over which is 3 over 26 take A2 is 6. Is that right? I think so.
Yeah.
8. 8. 36. 26. 18, take 10, 8. 3/8. So that's telling us that over here we've got a point there. So that then suggests to me this goes like this. So then if I follow that back, if that bit goes like this, and it's above the axis down this end, cuts the axis here, that suggests to me that we're going like that. And then if I'm going to follow the same pattern, looks like that. Does that make sense, what I've done there or not? Let me draw a graph of it then. Here we go. Up the top, just so x minus 3. Over x squared minus 3x minus right, there it is. Right, one more example. Right, so I just chose x equals 6 and figured out where that is. There are other ways of figuring out where all of that is, but those would be kind of a bit more time consuming. All right, last example. So again, this is undefined if x squared plus 2 is equal to 0. So undefined. So when x squared is equal to -2, or where x is plus or minus the square root of -2. Which we can do, we're specialists, we know about complex numbers, we can find the square root of -2 if we want to. However, these graphs that we're doing on the Cartesian plane is restricted to the real number set, yeah? So Cartesian plane is real numbers. This would be an imaginary number, so there's no real solution. Right, it's not an Argand diagram, it's a Cartesian plane, only real numbers. So if there's no real solution, so there's no vertical asymptote. Alright. So this one's a little bit more complicated to figure out what's going on. So let's look at some intercepts. Alright. Again, there's no number on here, so it kind of suggests there might be a horizontal asymptote at x equals 0. So at y equals 0, not x equals 0, what I'm talking about. Y equals 0. So there's that suggestion. All right, let's look at for some y-intercepts. X equals 0. And so y-intercept when x equals 0, 0 plus 2 over 0 squared plus 2, which is 1. Is that right? Am I right there? Yep. Am I right there? X-intercepts, y equals 0. So if y equals 0, 0 equals x plus 2 on x squared plus 2. So x equals -2. So again, we've got a situation where our asymptote's not always an asymptote. Cuts through the asymptote. All right. Now, where are we? We draw my put in. So we know we're going through y is 1, x is -2. And then the question is, what's happening down here? And what's happening down here? Because it kind of looks like it's going something like that, between those points, something like that. But the question is, what goes on down here? You know, does it keep going up here? What goes on here? Does it keep going down here? So we need to test that some way or other. So, another way, rather than picking some numbers, another way of testing is doing this. So up here, as x is tending to infinity, y is tending to, so what you can say is, all right, infinity plus 2, the plus 2 is really of no consequence. Infinity squared plus 2 again, the plus 2 is really of no consequence. So then you've got infinity over infinity squared, and if you, the mathematical thought process cancel that out, it's the same as 1 over infinity. So 1 over is a massive number, is heading towards 0, Aaron, well done. Heads towards 0. So down here, as x is getting bigger, the y value is heading towards 0. So that's suggesting that this is somehow got to curve around and head back down there. And so up here it's an asymptotes. Yes, no, maybe. Now, then what's going on at this other end then? So as x goes to negative infinity, following the same thought process, well, then y is going towards negative infinity squared. That's a positive number, isn't it? Positive infinity squared. So it's going to negative 1 over infinity. And again, that's going towards 0. But this negative means it's going towards 0 from the negative. It's coming down here. So it's going from negative. Whereas up here, so that was from positive. All right. So that's another technique that you can use to kind of figure out where that graph's going. And so there it is, like so. Something like that. Any questions about that? There's a couple of things in there that you might not be overly familiar with.
That's new, yeah.
That's new? This thinking's new? Yeah. And it's just like we use infinity as, think of it as a number. So deal with it as a number. So if you've got some massive number and you're adding 2 to it, effectively it's still that massive number. Treat it as a number when we square it, infinity squared. All right, let's treat it as a number. And then we've got some cancelling. And then we say, okay, well, what does that mean? If that's a massive number, 1 over massive number is a teeny tiny one. So the bigger you go, the smaller that's getting, so it's going towards 0. It's talking about negative here, so it's going towards 0 in the negative. So it's just a thought process that you can use to see whether it's asymptotic or whether it's not. All right, because if that was going towards infinity, for example, not towards 0, it would head down there. Yep. All right, do you want to put that on there?
Yeah.
You do? All right, let me put that on there. X plus 4 plus 4 plus 2 plus 2.
It's on the top as well, X plus 2.
Oh, plus 2, not 4. Yeah. There it is. All right, so that turning point that's there, like I haven't quite got that. So you would have to use calculus or whatever to find that turning point. And down here, and this, it looks like it's on the axis, but if I zoom in, you see it does cut through. Swing back. All right. Oh, there is one more. There's one more example. Sorry, I lied. No. Asymptotes, not always horizontal. So let's have a look at one where they're not horizontal. Oh, we still follow the same things. So, example. Alright, x squared plus 1. X can't be 0, so undefined. And x equals 0, there's no cancelling out because you can't factorise that. So we've got an asymptote. Because this power is less than the power up there, we've got to divide it out or separate it out, whatever technique. One like this is, because I've only just got the x there, it's simple enough to go like that. So here we've got y equals x plus 1 on x. So here it's like a combination of y equals x and y equals 1 on x, yeah? We separate those out.
Yes, I know.
So that's where we get our asymptote that's at an angle. Because this bit here, as x gets bigger, this bit gets smaller, and we just go towards y equals x. And the same if we go in the negative direction. So from this, as x goes towards infinity, that's going towards infinity plus 1 on infinity, which is just going towards infinity, which suggests it's going to just towards y equals x. Alright, because x was infinity. And the same if you work the other way. So what that actually means is that you've got our asymptote is y equals x. So when we draw that, we've got an asymptote that goes so. Again, there's no plus 0, there's no plus some number on the end, so we've got a horizontal asymptote at y equals 0. X equals 0, vertical asymptote. We know that. Sorry. From x equals 0, we've got that vertical asymptote there, what I'm talking about. Ignore that last bit. The horizontal asymptote is not horizontal anymore, it's been twisted. This one, I forgot to put in X there. So the question is, whereabouts is our thing go? Any ideas? Right, because we've got a section here, section here, section here, another section down here. So the question is it there and there or here and here? Any ideas? No ideas how we can find out. X-intercepts, y equals 0. 0 equals x squared plus 1 over x. 0 equals x squared plus 1. Negative 1 equals x squared. Again, no real solution, is there? So if there's no real solution, that means no x-intercepts. So if there's no x-intercepts, it can't be here and here, it's got to be here and here. Like so. That's terrible. You want me to do that on the calculator? So on the calculator, what do we have? X squared plus 1 over just X. There it is. All right. That's it. We're done. Except the textbook doesn't have this in the textbook, so I've got some